everyone, my name is Mayank Jindal. Thank you for joining me today on designing scalable and reliable AI systems with microservices. Little bit about me. I work as a software engineer in Bay Area. I have focused on building AI-powered scalable software. In the past, I have been an open source contributor, and formally, I have a master's degree in computer science from University of Chicago. Little disclaimer, the views and opinions expressed in this talk are personal and do not reflect the official policy or position of any other agency, organization, employer, or company. So this is the agenda of today's talk. First, we will talk about what are AI systems. Then we'll talk about microservices. Then we will talk about a sample microservice architecture, then communication patterns, fault tolerance, performance optimization, effective collaboration, and in the end, we have some time for Q&A. But please feel free to me to stop and ask any question. So let's start with AI systems. What are AI systems? AI systems simply are software systems that leverage artificial intelligence to learn from data, recognize patterns, make predictions, and automate decision making. There are few major components of AI system. One is data collection and processing. In this component, we fetch data, clean data, and prepare the data for the later stage, which is model training. So in this stage, we train the model and we evaluate the model to see if we are having appropriate accuracy so that we can deploy those models to production and we can make some inference. So the third step is basically inference and decision making. And the last stage is continuous improvement. So this is kind of optional, but it helps maintaining AI models accuracy and performance over time. Now, there are some unique challenges of AI system. First one is computational resources. AI models require extensive computational resources, unlike a basic software system. For example, we might need to use GPU to make AI model inference faster. Another challenge is complex AI workflows. AI application consists of multiple stages like data ingestion, pre-processing, training, validation, and inference. And these stages require easy integration among them. The third challenge is data intensity. AI applications rely on large volumes of data, and that large volume of data must be efficiently stored, processed, and retrieved in real time. The fourth is dynamic model evaluation. AI systems might need continuous retraining so that we can make update in those AI models, and it is not often required in traditional software applications. Now, there are few things like versioning, rollback strategies, and model drift management, which can be very useful to integrate in the entire architecture. And the fifth challenge is fault tolerance and resilience. Now, there can be many different kind of errors in AI services, like model errors and hardware failures. So we need to ensure that we have enough failover mechanisms and we have resilience strategies in place so that entire architecture can run without any interruption. Next, we will talk about microservice. So microservice is one of the architectural approach to software development. In microservice architecture, a large application is separated into smaller independent parts, and each part has its own responsibility. Each part runs independently with its own business logic, database, and API. Now, to serve a single user request, a microservice-based application can interact with many internal microservices to form its response. So in this picture, we have a monolithic architecture on the left side, where all the components like user interface, business logic, and data access layer, database, all of these is included into one single stack. But in the microservice architecture on the left side, we have different microservice for interacting with different components. and each component has its own database, its own business logic. Now, let's talk about microservice and AI system. Since we have seen that AI system composed of many different components like data preprocessing, model training, inference, so we can create one microservice for each specific task. Like for fetching, cleaning, and preparing the data, we can create single microservice, and another microservice can be for training the model and evaluating the model. Then we can have third microservice, which can be used to deploy to production and monitoring the model or collecting data or any kind of evaluation. Now let's talk about benefits of microservice. So the first benefit is scalability. Since each microservice can be independently scaled, so it will meet application demand better. And it also helps maintaining availability because let's say if a service experiences a spike in demand, then that service can scale independently of other microservices. Like for example, let's say there are a lot of requests which needs to be routed to inference service. Then that inference service can be scaled, and other services like data pre-processing, cleaning, fetching the data, those doesn't need to be scaled. Next is organizational structure. Since we will have different microservices and each microservice will have its own responsibility, we can create small and independent teams which can take ownership of specific services. And each team will act within a small context, and each team will have more skills to work more independently and more quickly. Since each team will concentrate on a particular service, they can solely own development, deployment, and maintenance without worrying about the complexity of entire system. And it also helps team member to make informed decision, iterate quickly, to maintain a high quality of service, since they don't need to worry about complexities of the entire architecture. Next is team productivity. Since a microservice has its own different small services, each team will have its own technological freedom. So, for example, different AI tasks might require different programming languages. Like data pre-processing might need the use of Java, whereas inference service might use Python. So, with the help of microservice, helpful to um, maintain different programming languages and different framework within each microservice. So it also shortens development cycle times because teams have more technological freedom.
I've got a question for you now. Would you mix together microservices and things like Data Factory in Azure to do the data cleaning?
Sorry, can you please repeat?
You use things together. Would you use some microservices and some things like Data Factory or similar kinds of services that you can obtain whereas it's system as a service rather than as your own implementation?
Yeah, we can definitely mix multiple components in a single microservice. So like, for example, in this picture, we have 7 different components. So it doesn't mean that we need seven separate microservice. If it might depend on use case to use case. Like for example, fetching, cleaning, and preparing the data can be fit into a single microservice. If developers feel that each of these components can use the same set of infrastructure, same programming languages, and similar kind of tools, then a single team can own a single microservice which can work on each of these 3 tasks. Does that answer the question?
Really, because I was asking about things like Azure Data Factory, which is a well-known kind of environment in which you can do data cleaning. ETL, that kind of thing.
Yeah, so we can have a single microservice owning that ETL, and that microservice can store the results in some shared place. from where other microservices can get that ETL data. Okay, any other question till now? Okay, so let's talk about other benefits. Like one is deployment ease. Since each microservice has smaller scope, it is easier to enable continuous integration and continuous delivery. And it is easier to try out new ideas and to roll back if something doesn't work. Now, this higher frequency of experimentation has lower cost, since if there is any failure in a single microservice, there is a huge possibility that other microservices will not be affected by that failure. And it is also easier to update the code. Now it also allows reusable components because we are dividing the entire software into smaller and well-defined modules. So teams can use those smaller modules for multiple purposes. Like for example, a translation microservice can be used for chatbot, and it can also be used for multilingual customer support and content localization if it is made generic enough. Another benefit is resiliency. It increases application resistance to failure. So in a monolithic architecture, if a single component fails, then it can cause the entire application to fail. But with microservices, we can degrade application functionality so that it will not crash the entire application. It also has the reduced risk associated with updates because any changes are made to specific service, not the entire system together. Now, I also want to talk about AI workflow orchestration because there are many different components like data preprocessing, feature engineering, training, inference monitoring. Managing multiple services is complex. So we can use some kind of orchestrator which can ensure that these services work together smoothly. So there are some key strategies for AI workflow orchestration. So first one is that we need to ensure that execution order is correct. Like a new machine learning model or AI model should not be deployed to inference until it passes validation stage and testing stage. So we can configure our orchestrator like first we will have validation and testing stage. After that only there will be inference stage. And another strategy is parallel and distributed processing for AI tasks. Now, we can have multiple model servers so that inference requests can be routed to those multiple model servers in parallel, and it will shorten the response time. The next strategy is error handling and fault recovery in AI pipelines. Now, AI models and services can fail due to many different kind of errors like timeouts, missing data, or any kind of computation. So orchestration can ensure that there are enough retries, rollback, and other kind of fallback strategies to prevent failures from breaking the entire system. For example, if a training job fails, orchestrator can retry or switch to the last stable version of the AI model so that it can give some kind of response. Now, speaking about fault tolerance, AI microservices must recover gracefully from any kind of failure. There should not be any kind of data corruption or any kind of disruption in predictions. Some of the common faults are model serving failures, like AI models may fail due to missing dependencies or any kind of timeouts during inference or any kind of mismatch in any data version. Another fault is data inconsistency. Feature engineering and model training pipelines, which is the previous stage of inference, that those pipelines might process old or corrupted data. Another is hardware and infrastructure failure. There can be many failures in GPU, or there can be a downtime in server. There can be network congestion. So all of this can disrupt AI workflows. Now, there can be cascading failures. So a single AI microservice failure can disrupt an entire system if dependencies are not managed properly. So we might have some dependency management like asynchronous communication, and all those things. So failures are not propagated to other microservices. And the fifth one is performance degradation. Now, AI workloads may slow down if inference latency is very high. So we also need to take care of that. Now let's talk about a sample microservice architecture. So we can, this is just an example. It is not source of truth. There can be many different ways of architecting an AI system. So in this, we are having a two-layer architecture. First one is a system integration layer, and the second one is model service layer. So client is not part of this architecture. Client will just talk to system integration layer. Now let's talk about system integration layer. So there are different responsibility of this layer. First one is transforming any raw data which we got from client request into a format so that that request can be passed to model service layer in the appropriate format. It also coordinates between services like invoking the AI model. It also handles timeout so that entire operation is smooth of the system. And it can also orchestrate requests across different models. For example, in the model service layer, we can have two AI models. Like first one is for text classification, another one is for sentiment analysis. And depending on the request, orchestrator can route the request to appropriate model. Now, once system integration layer gets response back from model service layer, it can post-process that output so that it is converted into a format which is suitable for end user or any other downstream applications. It can also have error handling and retries, like let's say model service layer call fails, so it can manage errors accordingly, or it can retry if reliability is necessary.
I'll ask a question there. Is that the same as what's called agentic AI? Is that integration layer or the orchestration layer? Is that representing some form of agent?
It is not exactly agent. So an agent is usually referred as like some system which can do like a lot of things. But here it is just a single part of the entire architecture, and it has its own defined responsibility, like pre-processing data, getting response from model. So it is more of a software system or technical system rather than a universal agent which can do every task from the, yeah.
I've recently been working on a system where we had 3 or 4 agents. You know, one would accept a request from customer from application, and then decide how it's going to handle that request and pass it to different agents to actually interface to the AI model.
Yeah, so I would say this is more of an architectural approach rather than a single entity like agent. And here we are having well-defined rules. Like we can have well-defined rules. Like first, it needs to pre-process. Then second, it needs to get response from model, and third and fourth like that. But in agent, like we don't need to give agent a well-defined instructions, I would say. It is more of a logical flow rather than rather than someone just tell the agent that do this. It is more of a software piece. But yeah, in like it also has a similarity to agent. Yeah.
So while we're stopped, I'd like to just ask regarding dietary requirements. I noticed that one person registered saying that they need no carbs, which I find difficult to satisfy with pizza. So we might have to pass on that one. Let's see how many we are. 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14.
Another one on the way.
15, 16, 17, 18 himself.
Caught in traffic.
Is there anyone here who's allergic to gluten or food intolerant to anything?
I'm allergic to egg.
Egg,
yeah.
Okay, I'll see what we can do there. Any other sort of special requirements? We always get some
Vegetarian on the way.
Yeah, we always get vegan anyway because the Domino's pizza is very good, and the plant-based ones. Number 19. Any special dietary requirements when it comes to ordering pizza? Thank you very much. Sorry about the interruption. Please carry on.
Thank you.
I have a question to you.
Yeah.
So I understand this more of a logical model. If I may ask you a question on the implementation side. So the client request for me, it seems to be more of a API management or some kind of API key. Does all your rerouting or orchestration or post-processing, for example, you mentioned post-processing, error handling, retries, more of a non-functional requirements for me. Do you think it's more of a API management in Azure, if you know Azure, rather than the microservice itself? What's your thought on this?
Yeah, so error handling, retries, and all of these things are related to API management rather than specific to microservice. So yeah, but microservice can also have all these things. But yeah, these concepts are not unique to microservice. It is more generic in software development. Yes.
So my question is it more for API management rather than you calling it microservice? That's my thing. It could be interchangeable as well. So I'm just asking if you practically implement something like this, what was your implementation was like, or was it like an API or Azure function or API-M?
Yeah, so model service layer can have its own API, and the system integration layer, which is in the middle, that will call that API. So that specific thing like error handling and retries, those are more of an API management rather than microservice only. So microservice just means that we are dividing this entire architecture into different components, and each piece is having its own like pipeline. Each piece can be scaled independently. So scaling is more of a microservice thing because we can independently scale this model service layer and integration layer. But yes, the error handling, retries, all of these things are unique, not unique to microservice.
Okay, thank you.
Any other questions?
So when you implemented the microservice, did you use APIs or something like that, or you go with the low lightweight Azure functions?
Yeah, we need to have some kind of communication between system integration layer and model service layer. So we will talk about communication more. We can have synchronous communication, or we can also have asynchronous communication through the message queue.
So my question is, implementation wise, did you use the API, Microsoft API, web API, or Azure function? It's more of an implementation question.
Okay, yeah, so implementation can be done through APIs. Like model service layer will have its own API, and then this middle layer can call that API and do the retries and error handling depending on the use case. Yes.
Thank you, Mayank.
Okay, let's talk about model serving layer now. So model serving layer is responsible for handling model inference request, and it is responsible for serving model predictions in the production environment. It is used as an interface between the AI model and other layer, and it ensures that AI model can be assessed in real time. It also ensures that AI models can be scaled to handle multiple requests efficiently, and it provides accurate predictions consistently. So it can have multiple things, like it can also pre-process system integration layer request if there is a need. Then it will do a model inference. Then it can also do a post-processing if it wants, and then at the end it will give the response back to system integration layer. So the first one is first responsibility is model inference, which is its core responsibility of this layer, and it will perform inference or predictions on the input data and return the results back to system integration layer. Like for example, given an image, there can be a model which will return a classification label like dog or cat. And another thing is model versioning and updates. So model serving layer can be created like to handle multiple versions of a model so that it ensures backward compatibility. It will also enable updates and any improvement to the model. And this layer should also support rolling updates where the new model is gradually rolled out without any downtime or disruption. Now, there are few design consideration, like the first one is scalability. A model serving layer must be able to handle any amount of traffic since AI systems might grow in uses. So we can have horizontal scaling, like adding more number of instances or adding more number of servers. We can also have auto scaling so that number of servers are dynamically adjusted based on demand to meet the traffic requirements. Now, also needs to ensure that model inference latency is minimal and throughput is very high so that user expectations is met for real time. Now, it also needs to ensure that it is resilient to failures and it can continue to function even if one or any other component fails. Like if one instance of the model serving layer fails, another instance can take over, which will prevent the downtime. It should also ensure any data security or privacy while serving sensitive data to AI models. So it can implement any encryption like TLS. It should also have access control to control the access on any kind of data. It can have data anonymization to protect sensitive information. Now, this model serving layer can be provided in the form of APIs. So APIs is a set of rules and protocols that allow one layer to interact with another layer. It acts as a bridge to allow different services and microservices to interact. Yeah. And the model versioning, let's talk about model versioning. Why is this important? Because AI models can evolve over time. So new version of a model can be deployed while the old version is still being used by other services or applications. Now, this API of model serving layer, it should be versioned to support multiple model versions at the same time. It will also ensure backward compatibility and it will avoid breaking changes for any existing users or system. So in the API formation, we can have clear versioning conventions. Like for model A, we can have v1/model A path and v2/model A path, so that upstreams layer like system integration layer can gradually move to a different version of the model. And similarly for model B, we can have v1/model B and v2/model B. Now let's talk about communication patterns. How can different layers of microservices can interact among themselves? So first one is synchronous communication, which is that any microservice must wait for a response from another service. It is more suitable for real-time applications that require immediate feedback. Now, another communication pattern is asynchronous communication, where client sends a request and it does not wait for an immediate response. It can be used using message queue. So in the synchronous workflow, upstream microservice layer send request, and then there is a request handler module, which can further send request to request processing module. Then processing module will give the response, and then at the end, handler module will return the results to upstream microservice layer. So before talking about asynchronous communication, I want to talk about message queue. What is message queue? It is a buffering mechanism which allows services to communicate asynchronously. So there are three main components in message queue. One is producer service, which will generate the messages and it will put those messages in the message queue. Another is message queue itself. It will temporarily hold those messages until a consumer process them. And then at the last, we have consumer service, which will take message from queue and it will process those messages asynchronously. There are few benefits of message queue. One is fault tolerance. So if a service crashes, like let's say entire consumer is not working, those messages remain in the queue and those messages will be retried later. Another is efficiency. So AI services won't block execution because of this message queue in between. These consumers can process those messages at their own speed. It can also prevent bottlenecks so that long running AI tasks can run independently without worrying about giving response in real time. So this is one example of asynchronous workflow. So at the very left side, we have an upstream microservice layer. It will send the request to request handler module. Then request handler module will put message in the message queue. And from that message queue, the request processing module will take messages one by one. And this taking messages from message queue is asynchronous. And then when microservice layer sends request to this request handler module, the request handler module will give the response instantly, and the response will just have a request ID. It will not give the entire results. And after taking messages from this message queue, this request processing module will run and it will persist, it will store those results in some kind of database, which will be indexed on the request ID, which is returned to the consumer, like my upstream microservice layer. And then after some time, upstream microservice layer can get results API, and that get results API call will go to handler module. This handler module will get the results from the database depending on the request ID, and that request ID should be part of get result API. Now, how would upstream microservice layer know that results are ready? There are two ways. One is that it can wait for some time. It can do some kind of polling, like get results at every 1 minute, or we can have some kind of notification system so that as soon as the results are ready, that notification component can notify the upstream microservice layer that, hey, results are ready. You can call the get results API. So any question till now before I go ahead?
So question on the synchronous workflow, what's the use case of the request handler module here? Because you can upstream microservice can directly call the request processing model. Right?
Yeah, these two request handler module and request processing module can be combined in a single system. I just added these two different things just to have consistency with this asynchronous workflow diagram.
Makes sense for us.
Yeah.
But yeah, okay, got it. Thank you.
Any other questions?
I got one. In the asynchronous workflow, would you be able to do similar to the message queue from the handler to the processing module, another one from the upstream service to the request handler to get the results? So for example, if the processing is done, you send a message back into another queue that is ready for process, sort of a notification.
So if we add a message queue here, then upstream microservice layer need to wait for some time. So let's say a request handler module takes message from that message queue after 5 minutes, then upstream microservice layer needs to wait for 5 minutes. So that will be that won't be a good strategies. So that's why this request handler module needs to be very fast. That like if it is getting the initial request, then it will return a randomly generated request ID. And if it is getting call of get results API, it will just fetch the data from that database and return the results. Does that answer the question?
Thank you.
Okay, any other questions before I go ahead?
Yeah, I do actually, and just pondering if there are other models around the get results piece of this. So this looks like the upstream microservices layer is is essentially polling the request handler to see if any results are ready. But I'm wondering if there is a more proactive approach where the request handler module sends when they're ready.
Yeah, so there is another approach which is having a notification system. So as soon as the results are present in the database, that request processing module can also invoke a notification component, and that notification component will invoke this upstream microservice layer, and that's how this layer will know that okay, results are ready for me, and then it can call get results API. So that is more efficient. But if you want to keep the architecture simple, we can use polling like call get results API at every minute. So both are valid approaches, and it depends on use case to use case. So we can send some kind of metadata in the initial request, and that metadata can be used to invoke to notify the right client in this microservice layer. So we need to have a notification layer in between after this request processing module. Does that answer the question?
Yeah, well enough. Yeah.
Okay. So let's talk about inference modes. Until now, we were talking about real-time inference, where model serves prediction on demand, typically with very low latency, like sub-second latency. But there is another mode, which is batch inference. So we can have some AI models which can process a large volume of data at once. So in this batch inference mode, we can have batch jobs, which are typically run on some recurring schedule, like hourly schedule or daily schedule. And it can allow taking advantage of different big data technologies like Spark to generate predictions. And these big data technologies might not be used in real-time inference just because of the low latency constraint. But it can be used in batch inference because latency requirement in batch inference is typically on the order of hours. So it also allows using models without worrying about strict latency. So we can use much heavier and much larger models because we don't have a latency requirement in the batch inference mode. And here, like we have an upstream component, it will send the request and it will have the same different steps like pre-processing, model inference, post-processing, and response. And once all of these things are finished, it will put the data into some kind of data storage, and from there upstream component can take the data. So there is no any low latency requirement in this batch inference mode, and it allows more freedom to model serving layer. So like, for example, we might have a AI model, which is very accurate, but that model doesn't have good latency. And that model might not be used in real-time inference, but that model might be used in batch inference. Now, talking about scaling, there are two kind of scaling patterns. One is horizontal scaling. So in horizontal scaling, we add more number of instances to distribute the workload across multiple systems. In this pattern, we add more number of machines to handle the additional load. Like for example, AI inference layer can have multiple instances or multiple servers so that requests can be routed among those instances and speed is increased. And also data preprocessing service can distribute tasks across multiple nodes in a single cluster so that it takes less time. Now, in the vertical scaling, we don't add more number of machines. We just increase the capacity of a single machine by adding more number of resources like CPU, RAM, or GPUs. In this pattern, a single machine is made more powerful rather than introducing any new machines. Now, for the scaling, we need to have some kind of coordination between API layer or system integration layer and model serving layer. So model serving layer is the component where inference requests are processed. Now, if number of requests increases, the system also needs more capacity to handle those requests. So speaking about the coordination, we need to have model serving layer scaled before the API layer is scaled so that there is enough capacity to process incoming requests by model layer. Now, in a hypothetical scenario, let's say if API layer scales without model layer scaling, then API layer might be able to handle more requests, but the model layer will become a bottleneck. So it will not give any benefit, and it will give some kind of delays or failures in processing. And requests might be queued up or rejected if model layer doesn't have enough resources to process those requests. Now let's talk about schema. So schema defines the structure of data like format, type, names of input output variables, and any kind of relationship between them. So in AI systems, a model consume input data and it produce output data. So over time, changes to these schema can happen. Like we can add some new features, we can remove some features, we can modify some kind of format, and entire system needs to adapt without breaking functionality. So on the left side, we have a schema pattern. So in this, we have different properties like first name, last name, and age. And we also have type of each of these property. Like first name is string, last name is also string, and age is integer. And in the right side, we have an example which corresponds to this schema. So we have an object of 3 variables, first name, last name, and age. And type of first name and last name is string, and type of age is integer. Now talking about schema updates, AI models evolve, data pipeline change, and system interface need to remain compatible so that there is no disruption in the operation. There can be many changes in input schema, like we can introduce additional input variables, we can remove or duplicate certain variables, we can modify the data type of existing variable, and similarly, there can be different kind of changes in output schema as well. Like we can add new output categories or classes, we can modify the format or structure of the output, we can rename the labels or fields in the output. So schema update gives a backward compatibility issue. Like if schema is changed, then it can break compatibility with existing models, data pipelines, or user-facing system. So let's say a new feature is added in the model input, but if the client application is not updated to send that new format, then it can cause some kind of errors in productions. So depending on the change, we can have few things so that backward compatibility issue can be avoided. Like if there is a new feature in the input, then we can provide some default values or we can handle some null values for that new features so that production system doesn't break. Like if there is any new feature like age group, then we can provide a default value like unknown for the historical data. Now, similarly, if we remove any features, then we can maintain compatibility by ignoring that feature, or we can provide some kind of fallback behavior for that missing feature. Like if, let's say, user location feature is removed, then we need to ensure that absence of this feature doesn't break the model. And we might also need to update the model training so that new schema is reflected in the model output. We can also change some kind of data type in the input schema. So if, let's say, feature was previously stored as an integer, but it is stored as a float now, so we can convert it during the pre-processing stage before giving that input to the model. Similarly, there can be multiple changes in output schema as well, like we can have new output classes. So in that case, we need to handle new output classes, and we can introduce a fallback mechanism for previous models so that previous model doesn't break in production. Like if there is a new category of classification model, let's say sports, then we need to ensure that a model can still output old labels because some of the clients might not move away from old labels. We can have some change in output format, Like we can, so in that case, we can include some kind of metadata, which will specify the schema of the response so that clients can handle those response of different formats appropriately. And like a recommendation system can output a list of items, and that output can have a metadata field like schema version. So based on the schema version, client knows how to parse the result. We can have that logic in the upstream layers. If the output variable is renamed, then we need to provide backward compatible values, and we also need to ensure that clients are notified of the change. Like if the model output variable is predicted rating before, but it is renamed to user rating, then the system should support both field names during the transition period. Now, there are some best practices of schema updates. First one is that we should allow versioning so that we can track changes and maintain compatibility between different versions of the model and data. We can also have schema registry, which is a centralized repository, and that repository will track schema definition and changes. That will store input and output schema in the registry, and then all the system components can use that registry. Uh, we will, for monitoring and observability, we also need to have these things in our AI system. So monitoring is simply about collection and analysis of metrics like response time, error rates to track system health and performance. Observability is the ability to understand the internal state of the system based on any logs, matrices, and traces. So AI system involve complex and distributed architecture, and in that architecture, performance and reliability needs constant tracking. It helps to ensure that AI models and other APIs and other microservices are performing as expected, like response time is faster and there is enough fault tolerance in place. There are some key aspects of monitoring. First one is metrics. So metrics is quantitative measure of any performance like response time, CPU usage, memory consumption, error rates, or any kind of inference latency. Logs are textual records which capture system behaviors, errors, and it can be used to help debugging and tracing any issues if they occur. Traces are distributed tracing, which tracks the request across various microservices to understand that how long each service takes to process request. And we can also have health checks, which are automated checks, which monitor the health of services. It ensures that entire system is up and running and performing as expected. So there are some key matrices which we can use in the system. First one is CPU usage, which is the percentage of CPU resources used by the AI model. Now, if this CPU usage is going above the threshold, then we can adjust the model size or we can offload some tasks to GPU. Another is memory usage. We can track amount of RAM utilized during model operations through this metric. If the memory usage is very high, we can do some kind of model pruning, or we can use some kind of efficient data structure so that our code or our business logic doesn't consume as much memory as it was consuming before. We can also track inference time, which is time taken to return a result after a request. So if this inference time is going way high, then we can optimize model inference. We can also simplify some computation so that inference time is reduced. Another metric is throughput, which is number of requests processed per unit of time. If throughput is very less, then we can increase compute resources. We can have some kind of load balancing. Another is error rate, which is percentage of request having errors. So if error rate is high, we can just simply debug and fix any kind of errors in model or any other business logic. And the last one is model accuracy. So if the model accuracy is very low or it is not expected, then we can retrain some model and we can do some kind of hyperparameter tuning so that we can deploy that newly retrained models to maintain the model accuracy as per expectation. Now, for error handling, there are few things like retries, timeouts, circuit breakers. So let's talk about retries. So So retries is a process of reattempting a failed operation, like API request, any kind of model inference. And there can be different kind of transient failures in the distributed system, like network timeout, service disruption, or any kind of unavailability of infrastructure. And retries ensure that these kind of temporary issues do not lead to permanent failures, and requests are eventually processed. So in this picture, we have an upstream layer which will do 3 attempts. So if the model server layer doesn't give response in attempt 1, then upstream layer will have attempt 2 and similarly attempt 3. So here we have set retries as 2, and in total there are 3 attempts. Now, when to use retries, if there are any temporary errors, then we can use retries. If there is any intermittent failures, then we can use retry. But let's say if there are any permanent errors, then we should not use retry. Because let's say if there is any invalid input or any data corruption or any misconfiguration in infrastructure, then even though if we retry 10 times, those errors will not be gone away. And it will also give unnecessary load to model server, and which can overload the entire system. And if the traffic is very high, then it will not be good for other requests. Now there are some retry strategies, like we can retry at a fixed interval, like we can retry every 5 seconds until the operation succeed. So in this picture, we have attempt 1 at 0 second, then attempt 2 will be at 5 second, then attempt 3 will be at 10 second. So there will be total 3 attempts, each as a fixed interval of 5 seconds. Now, but this frequent retries can overload the network bandwidth, and it can also cause contention, because if every client is retrying at every 2 seconds or 3 seconds, then there will be a lot of requests on the model, which will not be good for other requests. So we can have some kind of exponential backoff. So instead of retrying at a fixed interval, we can retry at increased intervals, like attempt 1 can be made at 0 second, and then attempt 2 can be made at 2 second, then 4 second, then 8 second, and let's say if there would have been attempt 5, it would have been at 16 second. So there is increased gap between each retry attempts. But the downside of this is that end user will have longer wait time. So it's a trade-off between wait times and more server overload. We can also add some kind of randomization, because even though if we are having exponential backoff, if each of the client is retrying at the same time, then model server will have contention that it will not have enough time to respond to each of the client requests. So we can have some kind of randomization so that each client does retry at different intervals. So like client 1 can retry at 1 second, client 2 can retry at 1.5 second, client 3 can retry at 4.5 second. So it will help avoiding the case where model server receives requests from each client at the same time. It will also help avoiding overloading the system. So this is one of the retry example in Python. So here we have an unreliable function, and this is simulated so that this function throws error 70% of the time. And we can have exponential backoff with jitter, which is just another name of randomization. So in this, we are having a while loop so that it is retry up to 5 times. We call unreliable function, which fails 70% of the time. If there is an exception, we use some kind of delay, which is randomization between 0 and maximum delay, which is exponential backoff, and then we retry after that time. Now, there are some best practices in retry, like we need to limit retries because retries are very selfish. If a client retry, it snatches away the server time from responding to another request. And it can also give overload to server so that server will overload and it will make matters significantly worse. Now we should use exponential backoff, as we have talked before. We can use some kind of randomization, And another thing is that we should set appropriate timeout values. So we need to make sure that retries are not infinite and we have some kind of timeout to break the retry loop. Any question till now before I go ahead? Okay, so let's talk about circuit breaker. Circuit breaker is another thing which we can use for error handling, which is useful in scenario for long-lasting faults. These kind of faults are scenarios where it is not useful to keep retrying because it takes a while back to hear back from the server, and it prevents an application from performing an operation which is likely to fail. It keeps a tab on the number of recent failures, and on the basis of any predefined threshold, it determines that whether the request should be sent to the server or not. So talking about mechanism, it has closed state. So if the circuit breaker is in closed state, then service is functioning properly, normal requests are processed. But if there is any failure, then circuit breaker will detect that timeout and it will track the failure. And another state is open state. Now, if the failure rate crosses a defined threshold, like let's say 50% of the requests fail, then circuit breaker will open and it will block further request to the failing service. It will also prevent the failing service from being overloaded by retries, because if the circuit breaker is open, none of the requests will go to payment service. Another state is half open state. So after a time, if circuit breaker is open, then it will enter into a half open state. It will check by routing a limited number of requests, and it will check if the service starts giving response. If those new requests succeeds, then it will go to closed state again. But if they fail, it will reopen and it will not allow any further request to go through the rightmost service. There are some benefits of circuit breaker, which is preventing cascading failures. It will avoid service overload and failures by blocking requests. It improves system resilience, and it also provides graceful degradation. So instead of having the whole system fail, circuit breaker will ensure that system can continue functioning. It will also have load reduction. Server not be overloaded if circuit breaker is open, unlike simple retries. So if there is any peak time of traffic, then it will avoid unnecessary load on the server. There are some best practices of circuit breaker that we need to set appropriate threshold. We need to have short timeouts, because if the timeout is very long, then it will not be good for clients. And another is that we need to monitor circuit breaker states, that how long circuit breaker was in closed state, how long circuit breaker was in open and half open state, so that we can better understand the health of the system and we can improve fault tolerance. Now, another mechanism for error handling is timeout. Timeout is the maximum amount of time which a system allows for an operation to complete before it is terminated or retry. It prevents the system from waiting infinitely, and since AI models and services often involve complex computations like model inference, data processing, timeout helps that operations can finish before it becomes unresponsive and it can waste any kind of resources. So for example, let's say here is upstream layer and it sends a request at t equal to 0 second, but we can set a timeout of 3 seconds, so that if there is no response from the model server in those 3 seconds, the connection will be closed and upstream layer will not wait. And through this, system can automatically fail if operation exceed the expected time frame. Now, there are two kinds of timeout. One is client-side timeout, which is initiated by the clients, which makes a request to the server. It prevents the client from waiting too long. We can also set timeout in the server side, which is timeout initiated by the server when a long-running operations exceed the allowed time. For example, like inference service might stop processing a request if the time exceeds the allowed duration. There can be different kind of timeouts like request timeout, connection timeout. So request timeout is the simple timeout that a system must wait for a response. Connection timeout is the timeout that system can use for establishing a connection to the service. We need to have appropriate timeout threshold, which we can set based on the expected duration of operations. We can have some configuration to handle timeout errors, like we can use retries or any other fallback models. We can provide some user notification if there is any timeout. So we can have some kind of fixed timeout that we need to have 5 seconds of timeout. We can have dynamic timeouts. So depending on the system load or depending on the complexity of operation, timeout can be set dynamically. Like for example, if there is for image processing task, if there is any larger image, then there will be a longer timeout. But if there is any smaller image, there will be a shorter timeout. We can have incremental backoff, same as retry mechanism in the timeout as well, so that if the system is under heavy load, we can increase timeout values because the server will have more time to respond in that increased load. So this is one of the timeout example. So we are having a request module and it sends a request to the model layer and it can have timeout of 3 seconds. If response is not received in 3 seconds, then this business logic will receive an exception and we can handle those exceptions accordingly. So there are some best practices like understanding operation duration. We can set timeout values based on the expected time of operation. We can use some kind of latency metrics of the downstream service to set the timeout duration. We should also monitor the timeout frequency to track how often timeout occurs. We should avoid overly short timeouts because if the timeout is very short, then there will be too many requests on the model server during the retry. And if there is any small increase in latency, then it will lead to a complete outage because all the requests will have timeout and it will start being retried. Another is fallback mechanism, that we can have a fallback in place like cache or any kind of default response when a timeout occurs. And we should also have testing and validation, that we should regularly test and validate the timeout under different load conditions. So let's talk about performance optimization. So this performance optimization is essential for low latency and high throughput systems. It impacts user experience and it also impacts operational efficiency and cost. So there are a few things which we can use to optimize performance. One is batching. So instead of making individual inference requests, we can batch multiple requests into a single API call. It will reduce the overhead from repeated input-output operations, and it will also allow models to take advantage of vectorized computation. So on the left side, we are having a 3 request. Upstream layer sends 3 requests, R1, R2, and R3 separately, but we can batch these requests together in the single call so that upstream layer will send all of these 3 requests in a single call, and model server will return response of all the 3 requests simultaneously. Another technique to performance optimization is model serving warm-up. We can have model servers warm by keeping those models loaded in memory. It will also prevent the need for reloading model on every request. So because reloading model can take significant time, depending on the model size or depending on the model latency. We can also reduce cold start latency because of this technique. So on the left side, we are having a model server which loads model from some other place during each request. But on the right side, we are having a model server which will have the model loaded in the memory so that during any further request, it doesn't need to take that model and it doesn't need to do that network call. It will not have any kind of network latency during other calls. We can also use caching for model inference. So we can use, if let's say same input data is requested multiple times, we can use caching so that it will avoid rerunning the model inference and it will return the pre-computed results. Now, for example, in recommendation system, if the user requests recommendation for a particular item multiple times, system can cache that recommendation after the first inference, and we can serve the cached result in subsequent requests. Now caching can also be applied for inputs which are similar rather than completely identical requests. For example, in a text-based AI system, if there is any small changes in the text input, like paraphrasing, it will result into same or very similar predictions. So we can use caching in that case. And now during high traffic periods, frequently requested data can be cached so that system can give that cached results back to its upstream layer. There can be any hot data, which is the input data which is frequently queried or is in high demand. Caching can be implemented for that kind of inputs to improve performance during peak times. Like for example, in a traffic prediction systems, if certain roads or areas are queried frequently, then system can cache the results for those roads and it will improve the response time. Another technique can be hardware optimization. So we can use right hardware and configuration to improve the AI performance. Like for example, we can leverage GPUs for faster model inference, since GPUs are specifically designed to handle the parallel computation, which is often a requirement of any complex AI models. We can also use model quantization, which is the process of reducing the process of reducing the precision of weights. So for example, we can convert 32-bit floating point weights to 16-bit or 8-bit. It can also reduce the model size. It will speed up the inference. It will decrease memory uses because model will be more power efficient. There will be some loss in accuracy, but it is often a trade-off between faster response time and accuracy. So on the left side, we have a base model which has 0.08 MB, and after the quantization, after reducing the weights, reducing the precision of weights, we can have model of 0.02 MB, just as an example. It has same layers, same number of neurons. It's just that the precision of those numerical weights is a little bit less. Another technique is model pruning. So model pruning removes redundant or non-contributory parts of model. It also reduces the size of the model like model quantization, and it will run faster and it will require less memory. So for example, we can reduce the number of layers in neural network if we determine that certain layers can have little effects on prediction accuracy. So like in this first layer and second layer has a lot of interconnection on the left side, but if some connections are not contributing to the accuracy, then we can prune those connections so we can have faster response time. Now, talking about resiliency, resiliency in AI system just simply means that system should continue functioning properly even when some parts of the system fail. So AI systems often involve large-scale deployments where multiple services interact among them. And a failure in one part of the system, like model inference API, can affect the entire system. So we need to ensure that services are available even during failures so that reliability and user experience is improved. So for maintaining resiliency, we can have some backup systems, which is standby system, which takes over if the primary system fails. Like for example, we can have some backup models so that if primary AI model is down, requests are routed to a simpler or lighter models. Like if a deep learning model for any prediction fail, we can just have a simple rule-based model or a lighter machine learning model. We can have some kind of data backups because AI models depend heavily on data. And if we lose that data, it can cause model degradation or failure. So we can regularly back up training data. We can store model artifacts. We can store some kind of predictions using some cloud storage solution or any other kind of storage solution. And then final thing is effective collaboration. So AI system typically involves multiple teams working together like data scientists, engineers, product managers, and business stakeholders. And those different kind of people, those different teams need to collaborate effectively so that AI development is successful and models are built, deployed, and maintained efficiently. There are some key aspects of this collaboration. One is team alignment, that we need to align teams so that everyone is working towards the same high level objective, and there are enough clarities around priorities and expectation. So we need to ensure that different teams stay coordinated through the entire AI lifecycle. And before starting the AI development, we should align on the end user needs. That, for example, one of the need can be that model need to be this much accurate. We can achieve this team alignment through various ways like regular meetings. We should set clear objective, and we should also define set roles for each of the team so that each team understand their own responsibility and how they interact with others. Another aspect is shared goals, that we should have shared goals and we should ensure that all teams work together that single shared goal. Each team should have a unified vision so that they can stay focused. It will also encourage joint problem solving when tackling some challenges like model performance, deployment, or scalability. There can be different kind of shared goals like business goal, that we should have a specific return on investment from an AI driven product. We can have some technical goals like model goals, that AI model should give this much performance, and that we can use any kind of metric to meet that performance like accuracy, recall, F1 score. We can have some kind of infrastructure goals, that AI system should be scalable, resilient, and it should be also deployable with high availability. We can have some kind of protocols. So protocols are clear and agreed upon process and communication channels which guide teams to interact throughout the entire project lifecycle. It helps team collaborate efficiently, reduce errors, and it ensures smooth transition between phases of AI development, like phase of model training to phase of model deployment. So we can have some version control protocols, like we can use Git to manage code changes, models, and dataset collaboratively. We should, for API design, we should define clear API interfaces between different system components, like model serving component and data ingestion component. We should also establish protocol for model monitoring, that how would the performance of any AI model be monitored. For communication protocols, we can use different things, like we can have regular stand-ups, which is daily or weekly meetings to ensure all teams are aligned. We can have some cross-team workshops to encourage cross-functional teams to work together on complex problems. We should also encourage cross-functional learning. So we can organize some kind of KT sessions or knowledge transfer sessions where different teams like team of AI engineers, team of business analysts, team of product managers, they teach each other about their work so that they can have enough understanding during the entire life cycle. And the next one is iterate and improve. So AI projects are often iterative. We should encourage teams to adapt and continuously improve. Like in the first iteration, let's say any AI model can have 90% accuracy, and depending on the feedback from business analysts or product managers, AI engineers can improve that model on certain use cases to meet, let's say, 95% accuracy bar. We can have some data sharing protocols. We should have some data security and privacy protocols so that if we work with sensitive data, there is enough access control on that data. We should have clear documentation so that data collection, pre-processing, and transformation steps are well documented and it is accessible to all the teams, so that if there are new people coming into the team, they can refer to that documentation and they can take help from that documentation. We should also have testing and validation protocols. So we can have some kind of unit testing, that before deployment, we should test the code and models. We can have some model validation step, which is that before rolling out those models in production environment, we can evaluate the model performance. And the final thing is bridging the gap, that AI teams often focus on technical model development, but there are business teams which focus on outcomes like profitability and customer satisfaction. And we need to align both the teams to make the AI project successful. So there are few steps which we can use to align AI and business teams. One is business feedback loop, that we can involve business stakeholders in regular testing and evaluation of AI models so that we can take timely feedback from business people that to make sure it meets end user needs. We can have some shared metrics. We can have some dashboard where shared metrics are displayed so that both the teams can agree on how success will be measured, and those both the teams can see those metrics weekly or monthly. We can have frequent check-ins, so we can hold regular alignment meetings to ensure that AI development is aligned with business priorities. That was all from my side. Feel free to ask any questions.
I was looking forward to this any demo or anything, Mayank.
Sorry, I couldn't hear you.
So what is there any demo or something like that? So for whatever you explained so far.
I haven't prepared any demo for this talk.
Are there any tools and technologies which are used for all of these APIs or models, or where you mentioned the retry patterns and all?
So we can use different cloud services if we want. So I know, like for example, AWS provides AWS SageMaker solution, which we can use for model serving layer. There are different other tools provided by other different cloud providers, which we can use. Like for API management, we can use API Gateway, and for data storage, we can have a object storage system like AWS provides AWS S3 storage. For ETL, there are different kind of tools for ETL as well. So yeah, depending on use case to use case, we can use different tools.
Last question. So is this based on what we really implemented, or is it a concept?
Sorry, can you please repeat?
Is this based on the real implementation you guys have done already in the project, or more of a conceptual?
So most of these things are based on my practical knowledge. But like, for example, this asynchronous communication pattern, which I showed before, and message queue, and that two-layer architecture, this request handler module, request processing module, upstream microservice layer. This is all based on my practical knowledge. But there are few things which I haven't directly used, like for example, this model quantization and model pruning, which I haven't had to use because like when I was working on AI project, it was giving enough accuracy and there was no any power efficiency issue or any memory issue. But these are the things which people often use.
It's also worth pointing out that in many cases, you don't need to train your own model because you get huge models like the Anthropic Claude, which are trained, and you just embed certain prompts within the query, tune what you get back. So that cuts out the entire model training step.
Yeah, so let me just go through this one. Yeah, so we can have this kind of cycle that we can have different steps in our model training. So the first step will be that we need to gather the data or gather the depending on what kind of model we are going to build. So let's say we are going to build any image processing module, then we can fetch those images and we can annotate those images, and that post-processed data can be fed to training the model. And once model is trained, we should align on the accuracy, that this training model is having 90% accuracy. We should take feedback from all the business teams. That is this 90% accuracy enough? And sometimes just accuracy is not enough, because we also need to see what are those 10% cases where model is failing. and are those failures enough for our business? So maybe we can avoid those 10% failures. So depending on the feedback of product managers or business people, we can try to increase the model accuracy, or we can keep the model at 90% accuracy. So once those models are trained and the feedback from everyone is taken and everyone is aligned on the performance of the model, then we can move to production stage.
Okay, I think we'll stop it there then. Thank you very much, Mayank, for a very interesting talk. What I think I mentioned to you that there is a sort of token of appreciation that we like to give, which is an ebook from the BCS library. So if you'd like to choose a title and let me know which one you'd like, we can make sure you get that.
Thank you. Thanks, Simo. Thanks everyone for having me today.
It's outside, so let's just thank Mayank for a great.